In this video, we're going to take a look at MPLS VPN routing, focusing specifically on the VPN aspect of LDP. So in the MPLS VPN forwarding mechanism, we're going to be taking a look at this in a very specific manner. The PE routers will label the VPN packets with a label stack. The LDP label is for the egress PE router as the top label, and the VPN label is assigned by the egress PE router as the second label in the stack. The results are the P routers perform label switching using the top label, and the packet reaches the egress PE router. The top label is removed. The egress PE router performs a lookup on the VPN label and forwards the packet towards the CE router. So as the traffic comes in, there's a VPN label assigned to the prefix that is advertised by the customer to the provider, and in order for the incoming PE to send the data across the wire to the other PE, there has to be a way for it to do that. The transport label is what happens. And as you can see through a lot of our trace routes already in the core section, we already took a look at how that came into play. We're going to take a look at how multiple VPNs will be coming into play, and you're going to have overlapping VPNs and multiple address or multiple customers connected to the same provider, things along those natures, so you can see exactly how it all comes together. Now, it says the top label is removed, and this is done in regards to the PHP process. So what is the VPN PHP process? PHP on the LDP can be formed on the last P router. The egress PE router performs label lookup only on the VPN label, resulting in faster and simpler label lookup. IP lookup is only performed once, and that is on the ingress PE router. He has to look to where he's got to go, and based off of that, there's a VPN label. The VPN label is built, and then to forward the traffic throughout the rest of the MPLS core, you place a transport label in front of the VPN label. You switch based off the transport label until you hit the PE router, or routers depending on the situation, that is connected to the PE router that is going to be your exit point out of the MPLS network. Once you've hit that, the PE router that is connected to the customer that you're trying to reach is actually advertising implicit null, which is a label value 0, which tells that's label 3. Label 3 is it's actually label 0 for that, so I've got them reversed. So the implicit null is telling the last provider core router to go ahead and pop the transport label and to forward the data via the VPN label. That's why you're going to see you'll go from a 2-label stack to 1-label stack and then to an IP stack. Once the traffic from the PE router gets to the provider core router gets to the PE router, then you peel out the VPN label and you route the IP. VPN label propagation. LDP is used to create labels and propagate them throughout the SP network. This is your transport label again. So the transport label is separate from your VPN label. Multi-protocol BGP is used to exchange customer routes and VPNs. Multi-protocol BGP extended communities, route distinguisher, and the route target are used to determine how to forward the VPN traffic. So you receive the traffic in from the customer, right? That information is then a VPN label is then associated. Transport labels are associated, and the labeled traffic then goes out to the network. Traffic comes in on the provider edge next to the customer that you're trying to reach, and then you reverse the process. A VPN label is assigned to every VPN route. The VPN label is advertised to all PE routers in the VPN in a multi-protocol BGP update. The label stack is built in the VRF table. The VPN label must be assigned by the BGP next hop, which is going to be your connection to the remote PE device. The BGP next hop should not be changed in the multi-protocol IBGP update propagation. So do not use the next hop self command on confederation boundaries. The PE router must be the BGP next hop. So you use the next hop self command on the PE router, which we have done in the past. The label must be re-originated if the next hop is changed. So a new label is assigned every time that the multi-protocol BGP update crosses the AS boundary where the next hop is changed. So I'm gonna hang out there for just a second. What they're basically saying is, when you're dealing with your inter-AS VPN configuration, you will have to reassign a new label per LSP, because that's going to be the important piece here. When we get into inter-AS option A, which is back-to-back VRF exchange, you're basically treating provider A is the first provider you go through. Provider B is the second provider you're going to travel through. The PE to PE connection is going to be handled as if it was a PE to CE connection, where provider A is going to be viewed by provider B as a CE and vice versa. Provider B is going to be viewed and handled by provider A like a CE. So what's going to end up happening is you're going to go in there and you're actually going to strip off the VPN information and forward based off of IP. And then when you go to the next PE router into the next provider, you're going to repopulate a VPN information, transport labels, and travel. That data is going to travel through their network the same way it did through the first network. It reaches the other end, and then it's routed via IP. So depending on the situation, and depending on how many providers you flow through, will determine how many different label switch paths you may have. Because you can do it back to back to back to back to back, and that will continue to go as long as the routes have been propagated the correct way. MPLS VPN and packet forwarding. The VPN label of the BGP route is understood by only the egress PE router. End-to-end LSP is required between the ingress and egress PE routers. The BGP next hop address must be IGP routes. LDP labels will be assigned to addresses in the global routing table. LDP labels are not assigned to BGP routes. So that's one of the big things that I want to make sure that everybody understands here, where LDP is used for transporting data from provider edge to provider edge. That's it. Same thing with traffic engineering. It's designed to move traffic throughout the provider core. BGP VPN v4 assigns a label value for the incoming customer traffic. So it's not LDP associating this, it's BGP associating the VPN label, and it's LDP or TE or BGP labeling that associates the transport label that gets the VPN route through the network. That is a big piece here that I find a lot of engineers have a hard time grasping. As long as you understand that part, you'll be way ahead of way ahead in your preparation, and I think you'll be in really good shape. BGP next hops announced in the IGP must not be summarized in the core network. So that what ends up happening here is you get into a case where you would break the LSP. Now we're not doing multi-area or multi-level routing, but basically you have to have a /32 loopback connection where R3 will see XR1's loopback as a /32 host route. If he doesn't see that, if he sees a 111.111.111/24, the LSP is going to be broken. Why? Simple. Because the R3 would be learning the XR1's loopback in as a /24 subnet, not a /32 host. So it's very important that you don't do any summarization anywhere in the network. Now, if you do summarization in the network, we'll take a look at this in more detail later on. The key factor here, though, is if you have a situation where you have a, let's say, for instance, I'll go flip over to our topology real quick. And let's say, for instance, you have a situation here where your connections to, let's say, this area right here, this is level 2, this is level 1, and this is level 1. Well, you have a multi-level implementation here, to where you're going to be sitting on here, you're going to be sitting the attached bit in ISIS, so you're going to be getting a default route from R2, and the attached bit will be set on XR3 towards R1. And the same thing will be happening up here on XR1 to XR2. You'll have the attached bit set on all these routers. So R1 and R2 will be the backbone, and XR1, 2, and 3, and R3 will be just the basically the stub areas. So you would have to route leak from the connections between R1 to R3. You'd have to route leak, or you'd have to route leak from level 2 into level 1 in order for R3 to be able to see XR1's loopback and vice versa. If you don't have that if you don't have that set up, you're going to have to get some sort of way of getting that more specific. Same thing with inter-area summarization with OSPF. You'd have to make sure that you aren't summarizing the loopback addresses to anything shorter than the /24. Or I'm sorry, anything shorter than the /32. If you're doing that, you could run into problems. We're not gonna demonstrate that, but just keep that in the back of your mind. So we'll take a look at moving forward in the configuration next, but I might throw that in as there as some troubleshooting, which I plan on doing because I'm going to be taking a bunch of stuff as we move forward here and troubleshooting some advanced configuration here. Once we get through the bulk of this course, I'll throw some troubleshooting scenarios at you just so we can test out what we've talked about and make sure that everybody's on pace for what we need to be working on.